So in the previous two lectures, we've looked at the behavior of free electrons inside solids. Delocalized electrons, electrons that do not belong to any atom because the atoms have been ionized. And we first of all, we looked at the k-space structure of these electrons. We derived the density of states for this sea of delocalized electrons. And in the second lecture on this topic, we covered the properties, certain properties of this sea of electrons. For example, using the Sommerfeld expansion, we were able to derive the dependence of the chemical potential on the temperature. We were able to look at the total energy content inside these electrons, and from there off we were able to derive the heat capacity. And the last example that we investigated in the previous lecture was finding out the magnetization of this sea of electrons. So was anyone able to compute the paramagnetic susceptibility? Of course no one. So all of the action, when you derive the paramagnetic susceptibility, all of the action yet again takes place at the Fermi level. So it is at the vicinity of the Fermi level where all the action is taking place, where all the conductivity is happening, where all the susceptibility is coming from. And the temperature of electrons at the Fermi level, the effective temperature is very high. It could be tens of thousands of kelvins, right? So, and all of this is happening because of the Pauli exclusion principle, because these are fermions and no two electrons can occupy the same level. No two states can occupy, not more than two states can occupy the same level. So at the most, two electrons can exist at the same level and they must have opposite spins. That's the Pauli exclusion principle. So it is because of the Pauli exclusion principle that all the k space points are gradually filled up. And at 0 Kelvin they reach the Fermi level, the Fermi sphere. And as the temperature changes, they kind of hover around the Fermi space a little bit, because the chemical potential has a very slight dependence on the temperature. So this is what we've learned so far. Now the electrons, like the phonons, are a really important excitation inside the solid, and many properties of the solids stem from phonons and from electrons and the mutual interaction between the electrons and the phonons. Superconductivity, for example, is a direct consequence of the interaction between phonons and electrons. So what we're going to see today is another aspect of the sea of electrons, and this is an answer to the question of what happens when this sea of electrons is placed inside a magnetic field. We've already seen one aspect, and that aspect is of polyparamagnetism. Because the electrons lie at the Fermi level, there is a susceptibility associated, paramagnetic susceptibility associated with those electrons, and that would be given by 3/2 the number of electrons per unit volume mu naught mu b square over kb Tf, if I am not mistaken. So this is the susceptibility of electrons, and it's paramagnetic, which means you apply a magnetic field, the magnetization develops parallel to the magnetic field. And notice that this susceptibility is independent of temperature. The Fermi temperature is a constant. So the susceptibility does not change with temperature for electrons. And so this is, as you notice, this is the Fermi energy. So I can write this susceptibility as mu naught mu b square over the Fermi energy as well. Okay. So this is the paramagnetic susceptibility for electrons. Yes.
So you physically can't count the paramagnetic susceptibility.
So this means that if I have a solid, I apply a field B, which is given by mu naught H, then the magnetization is going to develop inside this medium M. Paramagnetism means that this magnetization is parallel to the field, and the susceptibility is a constant of proportionality between the applied field and the magnetization. Okay. So this means that higher the Fermi energy, smaller will be the paramagnetic susceptibility, but the susceptibility is independent of the temperature, and this susceptibility is non-zero. And why does this susceptibility appear? This susceptibility appears because in the absence of a magnetic field, both the spin up and the spin down bands are at the same Fermi level. They overlap, they coincide. This is my density of states axis, and this is my energy axis. However, if I apply a magnetic field, the electrons with spin parallel to the applied field, for those electrons this band shifts lower in energy, and for the other kind of electrons with spin in the opposite direction, the bands shift, their energy goes up, and some redistribution of the electrons takes place in the vicinity of the Fermi level. All in all, at the end of this application of a magnetic field, there will be more electrons with spin up than with spin down, and the population difference will impart a magnetization to that material. So this is how this susceptibility is showing up. For electrons or spins that are bound to the atoms, so these are free electrons. So if you have, for example, a salt like copper sulfate, you have positively charged cations inside that salt, copper plus ion. So there will be electrons inside this copper ion, but those electrons are bound to the copper atom. So those electrons, if they are unpaired, since this is a d orbital element, the electrons are in the d orbital for copper, those electrons will be unpaired, but they will be firmly hooked to the copper atom. So those will not form a sea of electrons, they will be localized electrons, but those spins will also cause paramagnetism. But that's not polyparamagnetism, that's another mechanism of paramagnetism. The same overall concept, but the paramagnetism will have a different form than this expression. Instead of the Fermi temperature, the normal temperature would appear for such salts. Okay? So for bound electrons, the susceptibility is inversely proportional to the temperature, to the ambient temperature at which that salt is placed. So if I make a plot between temperature and the susceptibility for bound electrons, this is what the graph looks like. So this is paramagnetic behavior for localized electrons. But in this course we are studying delocalized electrons.
Delocalized is called polymagnetization.
So this kind of paramagnetism is called polyparamagnetism, and it happens for electrons inside metals. These electrons are delocalized. Now all of this is paramagnetism, but there could be another kind of magnetism which is called diamagnetism. In diamagnetism, you apply a magnetic field and the magnetization is developed in the opposite direction. In a classical sense, this is due to the Lenz's effect, the Lenz's law. When a field is applied, the electrons will start revolving around the field in a direction such that the magnetic field created by the revolving motion of the electrons, the orbital motion of the electrons, is going to oppose the applied field. So magnetization develops opposite to the applied field. This phenomenon is called diamagnetism. Okay? So Diamagnetism is a very weak effect. It's a tiny, tiny effect. But all materials are diamagnetic at the very heart of it. In paramagnetic materials, the paramagnetism outweighs the diamagnetism. Okay? Can you name the strongest diamagnet that can be found? Iron is not diamagnetic. Iron is a ferromagnet. Copper is weak. Copper, in fact, is paramagnetic. So the strongest diamagnet that has yet been discovered or synthesized is a superconductor. A superconductor is a perfect diamagnet, which means that if you put a superconductor inside a magnetic field, so you have this palette of a superconductor, you put it inside a magnetic field H, currents start flowing on the surface of this superconductor. Surface currents such that inside the superconductor an opposing field is developed. M is developed which is opposite to the applied field, such that the overall field inside the superconductor becomes 0. Okay? So it's a perfect diamagnet, and that's why this superconductor levitates when placed inside a magnetic field. Okay? So a superconductor is a perfect diamagnet. But today we're not going to look at superconductors or materials, these exotic materials of this kind, because we still haven't fully understood electrons and phonons. What we're going to study today is a form of diamagnetism which is unique to solids, and it's called, and the effect that we're going to study today is called Landau quantization. So today's lecture is primarily about Landau quantization. And Landau quantization gives rise to a diamagnetic effect. Okay, so let's begin our expedition into Landau quantization. And this is also the beginning for a study of exotic quantum Hall effects inside two-dimensional materials. So generally this topic is not covered in conventional condensed matter first courses on condensed matter physics, but I would like to give special attention to this. And this is the first time we're going to see the electron's behavior inside a magnetic field. So far we haven't talked about magnetic fields inside this course. So the magnetic field is a stimulus, and we're going to see how the free electrons are behaving under the response of that stimulus. Let's talk about free electrons inside the metal. So if there is no magnetic field and we have these free electrons, there is no potential that these electrons see. So there is going to be a Hamiltonian. What is that Hamiltonian for free electrons?
Kinetic term.
Just a kinetic term. Right. So this is the Hamiltonian for a single free electron. One single particle Hamiltonian. Right, just one particle. And the eigenfunctions corresponding to this Hamiltonian are simply given by plane waves. Correct? So this is just for an electron that is not inside any stimulus or any magnetic field. Now we impose a magnetic field. Suppose the magnetic field is B. It's a vector. So when you have problems of this kind quantum mechanically, what you would like to work with is not the magnetic field but a potential which is called the vector potential. Magnetic vector potential. So corresponding to B there is a magnetic vector potential. And that vector potential is defined such that B equals the curl of the vector potential, which is denoted as A. And why can we define the magnetic field in this fashion? We can define the magnetic field in this fashion because we know that the divergence of a magnetic field is 0, Maxwell's equation, and we know that the divergence of a curl of something is 0. This we know from differential geometry. So we do know that the divergence of a curl of something is 0. So we can define our magnetic field to be the curl of a vector potential. Now magnetic fields are real, they have real impacts, electric and magnetic fields. They can be measured, for example. The forces due to electric fields can be measured. The torques due to magnetic fields can be measured. So the real things are the electric and the magnetic fields. So we have to reify electric and magnetic fields. But this vector potential is an abstract concept, and there is some choice that you can make in selecting an appropriate vector field. Okay? So that choice is called the choice of gauge. So that choice is called gauge. The choice is the gauge. So different kinds of gauges can be chosen. Now suppose our magnetic field, now this sea of electrons inside the solid is subject to a magnetic field that points in the z direction. Let's say. So one choice of A, there could be many choices of A. So the gauge that we choose is the following: A equals minus B y in the x direction. This is our choice of gauge for this particular problem. We can also choose other gauges. So there's nothing special about this. We could also choose Bx along the y direction. We could also choose a combination of x and y. We can choose a symmetric gauge as well. So this gauge that I am choosing to exemplify this problem is called the Landau gauge. And you can check that if this is my definition for A, this is satisfied. You can check that. Okay, so this is my choice of gauge. Now when I have a magnetic field, the momentum, this momentum is going to change. In the presence of a magnetic field, the momentum changes from P to P plus the charge on the object, on the particle A, P plus QA. And the Hamiltonian, this is how the Hamiltonian is readjusted in the presence of a magnetic field. In our case, the charge on the particle is, it's a negatively charged particle, its electron is minus E. So we have to replace the P by P minus EA. Okay, over here. Okay, so what this term is going to do, the magnetic vector potential is going to give orbital motion to the electron, as we will see in a minute. Okay, yes please. No. We have chosen an asymmetric gauge. We could have chosen another, so we could have chosen a symmetric gauge of this kind. A could be equal to B crossed with R. This is a symmetric gauge. We could choose this gauge as well. This is called the Coulomb gauge. Okay. Now, with the Landau gauge, how is our problem readjusted? So our problem is readjusted by noting that in the presence of a magnetic field, the Hamiltonian becomes P minus EA whole square 1 over 2m. Okay, so this is our new Hamiltonian. But there's an additional effect that's going to occur. What is that effect? What is missed out in this Hamiltonian? Remember that the electrons are spin half particles. So there is a Zeeman interaction. There's an interaction of the spin of the electron, the spin half of the electron with the field. And there is a Hamiltonian corresponding to that as well. That Hamiltonian is, as we've seen in the previous lecture, is minus mu b. B, the strength of the magnetic field, and the Z Pauli matrix, because the field is applied along the Z direction.
Spins aren't interacting with each other.
They're not interacting with one another, they're interacting with the field. The electrons are non-interacting, but they are interacting with external stimulus. So this is this will explain the orbital motion, and this is called the Zeeman effect. When you place a spin inside a magnetic field, it either aligns with the field or anti-parallel to the field. Okay, so this is now our Hamiltonian, and we would like to see what kind of energy level diagram comes out from this Hamiltonian in the presence of a magnetic field. So how do the energies of the electrons change, and what is the corresponding density of states for the electrons in the presence of a magnetic field, and how does that impact the properties of the electrons, notably the magnetic properties and the electrical properties of the electrons. So this is what we're trying to find. We're looking for the electronic and the magnetic properties of the electrons inside the magnetic field, right? Okay. So let's move forward. So this is a vector operator. It will have an x component, a y component, and a z component. Now A only has an x component with the Landau gauge. So this term will have an x component, a y component, and a z component. So if I expand this term in terms of its components, I will get 1 over 2m px. A is now minus by. So I think I've made this. This is p. This can be. It will work with minus as well, but let me put plus here. Minus here. Can a plus here? Okay. It will work otherwise as well, but let me conform to the convention. This is minus. This is plus. This is plus. Okay. So this term will become, as far as the x component is concerned, minus EBY whole square. This is the x component of the canonical momentum, because I have replaced A with minus by. Okay. This y is another operator because I am dealing with operators. Plus there is of course a y component as well. There is a z component as well. The magnetic field applied along the z direction has only impacted the x component of the momentum operator. This is an operator. So is this. This must be an operator as well, right? With a different choice of gauge, this component will be impacted. But the energy level structure will be unchanged, because the energy level structure is real. So these three terms take care of the first term here, the kinetic energy term, plus we have a term corresponding to this minus mu b B sigma z. Okay, so this is our Hamiltonian. And if we would like to find out or write down or propose an ansatz for the eigenfunction corresponding to these electrons. Now notice that the only coordinate that exists in this inside this Hamiltonian is y. That's the only coordinate that exists. As far as z and x are concerned, we do not have an x coordinate and we do not have a z coordinate. We only have a y coordinate as far as the position coordinates are concerned. Okay, we do not have a position x, we do not have an x operator or a z operator. That's why the wave function will be an ansatz, a suitable ansatz would be a plane wave along the z direction and a plane wave along the x direction. So EI kxx, EI ky y, sorry z, kzz, and some arbitrary function of y is needed because of this y operator. Let's call that arbitrary function phi of y. So this is a suitable ansatz, and when you in the Schrodinger equation, in the time independent Schrodinger equation, you have the Hamiltonian, this wave function, this ansatz. This will give us the energy for a particular quantum state with a particular value of kx and kz. So this is the time independent Schrodinger equation. Now we could just do something really interesting here. If I look at the Hamiltonian, I take EB as common. So I put EB, I take EB, factorize out EB. I'm left with this Px over EB minus y, right? EB, E square y minus plus Py square over 2m plus Pz square over 2m minus mu b, b sigma z. All right? Yes.
सर आपने जो वेव फंक्शन लिखा है बस आप इग्नोर कर रहे हैं स्पिन वाले पार्ट।
इसमें कोई स्पिन वाला पार्ट भी होगा, ठीक है, स्पिन वाला पार्ट भी होगा. So this is my Hamiltonian, all right. Now what I could do now is let me set Px over Eb is an operator. If I have this operator Px acting on psi, what do I get? Px acting on psi is minus iota h bar ikx psi, correct? So this is h bar kx psi. So psi is indeed an eigenfunction of the Px operator, this operator here. All right. So what I could do inside this Hamiltonian, I could replace this Px over Eb by another operator. Let's call that I can replace this since psi is an eigenstate of this operator, instead of the operator I can write down the eigenvalues. I would like to write down the eigenvalues. I can do that if I wish to do so. I could also replace this operator and give it another symbol, say y naught, and put a hat on top of it. Y naught is just a symbol for px over eb. Okay, so what I do in the next step is I write my Hamiltonian as h equals e square b square over 2m. Since this is a square, I can kind of invert the signs, y minus y naught whole square plus py square over 2m plus pz square over 2m minus mu b b sigma z. All right. I can also write this as e square b square over 2m y minus h bar kx eb whole square plus py square over 2m. Write these together, followed by pz square over 2m minus mu b b sigma z. Now let's see what's going on. If I were to look at this term inside the Hamiltonian, what does this term resemble? To what physical system does this term resemble? ये कौन से फिजिकल सिस्टम का हैमिल्टोनियन है जो हम बार बार पढ़ते आए हैं? It's the Hamiltonian for a harmonic oscillator, right? So this represents the kinetic energy term for a harmonic oscillator. This represents the potential energy term for a harmonic oscillator. And the potential energy term is such that if I were to plot the potential energy manifold, so if this is my y, so corresponding to this operator, the eigenfunction for this operator is just the variable y. This term will lead to a potential energy manifold which is parabolic. The only difference is that its minimum will not be at 0, it will be at y naught. And what is y naught? The value of y naught is h bar kx over eb. The momentum along the x direction over eb. Right? So the potential energy curve corresponding to these terms, which I put in a yellow box, is simply of this kind. This point is h bar kx over eb, depends upon the magnetic field. So this is a diagram of the effective potential energy which this electron is seeing when the electrons are placed inside the magnetic field. Okay, and from this I can now what does the energy structure for a harmonic oscillator look like? Equally spaced levels, right? Equally spaced levels, right? Spacing between these levels. From this expression, what can you tell about the spacing between these levels? What should be the spacing between the levels? So this term over here, this, sorry? E square b square क्या है? स्पेसिंग है लेवल्स की, देखो ना ये है मोमेंटम स्क्वायर ओवर 2m. So the harmonic oscillator has, if I put the harmonic oscillator's Hamiltonian, this looks like this: p square over 2m plus half m omega square sum y square, right? Half m omega square y, right? And the spacing between the levels will be h bar omega if this is the Hamiltonian. H bar, this omega will be the, so this term over here is half m omega square equals e square b square over 2m. Let's see what omega turns out to be. Omega turns out to be EB over m. Correct? Let's call this omega omega c, cyclotron frequency. Why am I calling this the cyclotron frequency? So EB over m is omega c. This has dimensions of frequency. Let's call it the cyclotron frequency. So this term is really akin to half m omega square if I make this identification. Omega c equals EB over m. If this is, and I'm going to explain why this is called the cyclotron frequency. If this is the scenario, then the spacing between any two adjacent levels in this manifold for the harmonic oscillator has to be h bar omega c. And this Hamiltonian itself is nothing, can be written in this form. H is h bar omega c क्या होता है L plus half, correct? So whatever I've written in the yellow box is really equal to this h bar omega c L plus half, where L is an integer that starts from 0, 1, 2, 3 all the way up till some maximum quantum number. So L is a new quantum number that has been introduced, plus of course we cannot forget the pz square term over 2m minus mu b sigma z. By the way, what I'm trying to do now is, this is h bar omega c. So since I'm writing Hamiltonian, let me write down this in operator form. The energy for the electrons is going to be h bar omega c L plus half plus, now the energy correspond, now this is a free particle with momentum along the z direction, because there is no other z variable anywhere, there is no other pz variable everywhere. So the energy corresponding to this term is simply going to be h bar square k z square over 2m, correct? And this term can be, the eigenvalue of sigma z, the Pauli operator, can be plus 1 or minus 1. So this term is mu b sigma z. Now I'm not going to write a hat on top of it, where sigma z can be plus 1 or minus 1 depending upon which spin we're talking about. So this is the energy for the electron. The energy for the electron is quantized by some quantum number L, and kz acts as a parameter, kz, and so does sigma z. So depending upon the spin of the electron and the kz value of the electron and which L does that electron lie in, this will be the total energy for the electron when placed inside a magnetic field. Now I'm going to look at the overall structure, the k-space structure as well. What does this physically look like in the k-space? However, I need to understand and describe why is this omega c. Why is this a cyclotron frequency? So we need some intuition for this. If I have an electron, it's in an xy plane and it's moving at a certain speed v, and I impose a magnetic field along the perpendicular direction b. So what's going to happen to the electron? Classically, just classically. हाँ बोलो बोलो हाँ, it's going to go around in a loop. It's going to go around in a circle. Some direction in a circle. Okay. So can I find the, so it's going round and around and around and around in a circle. That's what happens in a particle accelerator as well, in a cyclotron accelerator. So if this electron is going around in a circle, now remember these are free electrons inside the metal, and this is orbital motion now. These electrons are now free to move. Orbital motion means that these electrons are free, they can go around in circles, physical macroscopic circles. Now what will be the angular frequency of this cyclotron motion? This motion is called cyclotron motion. What would be the angular frequency omega for this motion? How will we derive the angular frequency for this motion? Simple classical physics, simple physics, A-level physics. Right, so what's the force? M v square over r, which is the centripetal force, equals the Lorentz force, EVB. Correct? So this means that my V equals E B R over M, which means that my time period to go around in a circle is the circumference of the circle 2 pi r over the speed EBR M. 2 pi m over EB, but the time period is 2 pi over a frequency, the cyclotron frequency. So omega c is EB over m, right? So this is a perfect motivation to use this definition, omega c equals EB over m. So now what we have in front of us is a Hamiltonian I should put A dagger A here. So this is our Hamiltonian and this is our energy level structure. This energy level structure is important. Okay, so now let's try to make physical sense of this energy level structure. Any questions? कोई सवाल?
हमारे पास जो एनर्जी की फॉर्म आ गई, तो आपने पहली चीज़ लिखी है, क्योंकि ये डिस्प्लेस का हैमिल्टोनियन, उसके उस फॉर्म पे कोई फर्क नहीं पड़ रहा, तो शो हमारे पास वही आ गया,
कोई फर्क नहीं पड़ेगा, सिर्फ एक फर्क पड़ेगा, वो मैं बताता हूँ. Now if you look at this term h bar kx over EB, h bar kx over EB is this displacement from the zero position. Now remember, this is y. This is a physical dimension, y, space dimension, and this object has some size, x, y, z. So the object itself, which we're going to discuss, which we are discussing, has some size. So there is a y-axis, right? And there's a length along y. So this point is Ly over 2. This point here is minus Ly over 2. So there are some physical dimensions associated with the object, and we know that the k space is quantized because of these physical finitude, this physical finitude. Because of this finite size of this object, the k space becomes quantized. Now this minimum of the energy, this distance h bar kx, must lie within the physical dimensions of this object, correct? So this h bar kx over EB must really lie inside minus Ly over 2, Ly over 2. Now if we did not have a magnetic field and we look at the structure in K space, we have discrete points everywhere, correct? So we have points for the electrons. This is what the reciprocal space looks like. And likewise we have this net in the z direction as well. And we know the volume of each infinitesimal K cube inside the K space, right? It's a small volume that is associated. Now if I look at what's happening to the K space, that this condition imposes another constraint on how big Kx can be and how small should it be. So the maximum value Kx can take is Ly over 2 Eb over h bar, and the minimum it can take is Eb over 2h bar Lx. So the Kx is constrained to lie within this range when you impose an electric field or the magnetic field onto the electrons. Sorry? So the total span in the Kx space, so you cannot take all values of Kx, they have to be bound from minimum and the maximum. So the total span of Kx is simply Eb, this is Ly, sorry, Eb Ly over h bar, correct? So there's maximum minus minimum. Now what is, so if I look at the y dimension, so this is the total span allowed for x, so that's it. So this is my Kx minimum, this is my Kx maximum, right? So this is Kx maximum, this is Kx minimum. Now how many Kx points exist in this one dimension? So what's the size of each K cube along this dimension? It's 2 pi over Lx. So each one of these distances, as we know, is 2 pi over Lx, correct? So the total number of points in this span of Kx, n, is this span divided by 2 pi over Lx. स्टूडेंट्स तो नहीं आगे, कितने हैं? ठीक है अभी. So let me just finish this. The total number of points that are in this axis. So I need to multiply this with 2 as well, because each K point corresponds to 2 electrons with opposite spin. So this turns out to be 2 Kx span is this E B Ly h bar Lx over 2, right? So I can cancel out this 2 and I'm left with Eb over h bar. Lx Ly is the two-dimensional area of this object. This is E phi over h bar. This is a 2 pi as well. So this becomes h. Now this is a flux. Field into area is flux. H over E is also a unit of flux. It's called a fluxon. Flux becomes quantized, and we're going to carry on this discussion in a week's time.